I were to say, when did this happen? And it involves at least the American West, you'd be pretty well off just to make a random guess and say Neogene, because an awful lot of this remarkable patchwork of stuff that we see here, it developed in the Neogene. The Neogene is the last more or less 24 to about 2.6 million years of geologic time. We used to say 1.8 for the Quaternary, but that's been extended back, taking a little piece back up. Interesting than when this was actually written, I think in 2005. The Neogene was used to encompass everything after. But now we do recognize the Pleistocene and Holocene as their own period. Again, because that's an old tradition. The Neogene was named by this guy, German guy, Ernst, who named it in 1853. The new recent, or something like this, it meant. And it's just two epochs, the Miocene and the Pliocene. Miocene starting around 24 million, and the Pliocene about 5.3 million years ago. Okay, lots to say about this, but maybe I'll hold because time is what it is. But you can see in the mammals, but also in a whole array of other groups, including birds and grasses and snakes and other things, there was a lot of evolution going on in the Neogene time. In terms of tectonics, it's almost unprecedented. The amount of tectonic activity around the world during the Neogene is just stunning. Just to point out a few things for our own continent, the Appalachians were rejuvenated quite strongly after having been worn down largely. The Sierra Nevada popped up, the Colorado Plateau pops up, the Basin and Range rifts open, a huge, I call it the Big Mitten, you can see it now as you see that. The Big Mitten is a huge area of volcanism that occurs also in the Neogene time. But let's turn to other more broad things just for a minute. Climatically, there was a period of stabilization. There was a strong cooling in the Oligocene. There were some small ice caps in Antarctica by this time. Miocene, stable, even warming a little bit before we go to later Miocene and Pleistocene, a very strong decline of global temperatures, as indicated one more time by the rise of del O18, the rise of the ratio of 18 to 60. Higher values, colder temperatures, and here you're in full-on glacial times, of course. Yes, it's an aragonite ocean. And we look at the world as a whole, it's pretty modern. Australia is coming into position, but this is middle Miocene. And you see a few things different, like Arabia is still pretty well snug up against Africa here. India was really in the process of colliding. Australia is a little southward, but you can see that much of the rifting had been accomplished starting in Cretaceous time. Now you have a series of plates as we see them today. Just one very critical note right here. The famous old Farallon plate. The Farallon plate had been all but destroyed by middle Miocene time. There's like one little remnant of it up here called the Juan de Fuca plate. It's a microplate. It's the last remnant up here. And the Cocos and Nazca plates down here. You can see they also lie on the east side of the Mid-Pacific Rise. And they're continuing to subduct. And they're continuing to have subduction here. But the old Kula plate and the rest of Farallon all swallowed up along this area and along this area. So you had this big continuous set of volcanism from the Aleutian arc of Alaska right down through here, but something critical has happened in this mid-stretch. We no longer have subduction along the coast of California. That has changed dramatically to a transformed mountain now. Otherwise, you see the ring of fire all around the Pacific, the Australian plate rapidly moving north eastward. Of course, Indian plate collided and then continues to sort of ram its way into Asia, and of course the Arabian plate here is migrating as well. Okay, let's put that for a moment and see. So let's just click off some of the different areas that were affected during the Neogene time. And during the Neogene, we see evidence for things going on in South America and many other places. Okay. Okay, just again, modern scene. Okay, so first of all, with this for a moment, and a couple of places to focus on, right through here. Of course, this is the Andes. The Andes proper are forming and continue to form as subduction of the Cocos and Nazca plates continues along South America. It's a standard, classic Andean style erosion. But up here, you've got some rather interesting things going on as the Caribbean plate evolves and develops through this time. You can see, by the way, that it's surrounded by tectonic regions. To the east lies the Antilles, that's A-N-T-I-L-L-E-S, Antilles Arc, which is where the Atlantic plate is being subducted underneath this funny little Caribbean. And on the west, you have a set of volcanism, volcanoes associated with subduction of the Andean Arc and so on. Okay, click for a moment, and you see this in a couple of scenarios. Back in the Cretaceous, there was wide separation of North and South America. There was a transform boundary which had shifted and sliced off pieces, which today are Cuba, Hispaniola, and Jamaica had been torn from the edge of Mexico, I guess you would say. And Nicaragua was up here. During the Neogene, this little piece migrates in on a transform fault to position itself to help form part of what is later to become a land bridge. This is modern, so there is a land bridge there. New volcanism creates an island arc through here which connects North and South America. And of course, there's continued eastward translation of pieces like Hispaniola, Puerto Rico, and Jamaica along this transform. And here you have the Antilles Arc. So this becomes a little isolated microplate called the Caribbean microplate during this time of the Neogene. As a part of the final connection during about the Pliocene, later Neogene time, Pliocene, 3 million years ago approximately, or maybe a little earlier, there was a continuous land connection re-established between the island continent of South America and North America. This had profound implications because it allowed a two-way street, really. Mammals came out of South America and moved northward all the way to Big Bone Lick, for example, the great big ground sloths, and armadillos and others, and possums, which remain the only real successful group that came out of there. But going the other way, there were large predators and elephants or proboscideans, bears and horses and llamas and cats. And many people have argued that this really did a number on the formerly isolated marsupials and primitive placentals that lived in South America, maybe so. This is called the Great American Interchange. There's some debate as to how important this was in causing the extinctions because many of these animals, even the primitive ones, lingered right on up to Pleistocene time. But those are things going on in South and Central America that you should be aware of, and they're all occurring in the Neogene. A new land bridge forms, the Caribbean plate breaks off from the Farallon plate and migrates eastward. There's a shifting of microcontinental pieces like Cuba and so on. Now let's move to the Old World and look at the, first of all, probably the Alpine Mediterranean region, and then to the Himalayas. So you see, the final closure of the Tethys occurs during Neogene time. The only pieces that are left of the old Tethys are the Caspian and Black Sea and the Mediterranean in here. They're sort of little remnant puddles left behind from the closure of this region, Africa, and also this region, India, with the Eurasian bloc. Okay? The closure of Tethys is a huge theme of the Neogene, as a sort of first order thing. Going back to the Alpine region, one of the last effects in the Alpine region, which was largely in place during the Paleogene, during Eocene, Oligocene time, but some of it lingered on into the Neogene. One was the rotation of Spain. Here's the Iberian subcontinent, and you can see it rotates here, opening up actually the Bay of Biscay, which is this area between France and Spain, and rotating Iberia in a position to close down the Strait of Gibraltar. This is the one place where the Tethys Ocean gets pinched really tight, and the last remnant is over in here, which is the Mediterranean. Of course, this involved a continent-to-continent style collision between Spain and France, really. And here you had a very interesting two-way situation where the Iberian subcontinent was subducting beneath France here, and you have, of course, an accretionary wedge shoved up on here, forming a peripheral basin in Spain, and on the other side, you fold the thrust belt, forming a retroarc basin. The result of this was a near closure of the western passageway of the Tethys. And what was left of Tethys was in a couple of branches, one to the north, where the Black and Caspian Seas are today, and the other to the south. This then became more or less fully enclosed basin, and during the late Miocene, there was a very strong climatic drying. There was a very strong aridity event, which is called the Messinian event, or the Messinian crisis by some people. And the Messinian event is named for an area in Italy, where this Messinian part of the Miocene is well exposed. What happened during the Messinian event is a fascinating story that was only discovered in the last couple of decades. We now know that there are huge evaporite deposits, that's halite, that's gypsum, and hydrite, underneath the Mediterranean Sea. There are even salt domes there. We know they date to the late Miocene. What happened in this time is that with a small drop in sea level and the drying of climate, that the Mediterranean basin dried up. We know that the Nile cut a huge canyon going much, much deeper because that was flowing down into a basin, and there were also similar passageways coming in from the east, coming out and draining the area which is today the Black Sea and so on. So this all boiled down by evaporation until you had just these brine pools down at a very low elevation with the continental area standing way up above. And then an amazing thing happened. This is a strange view, but bear with me. This is the Strait of Gibraltar here. This is the Atlantic Ocean, and there's the near-dried Mediterranean Sea. Somewhere around 5 million years ago, during the late part of this event, there was a slight sea level rise, which caused a colossal flooding. Probably one of the world's largest waterfalls ever, carrying salt water, Atlantic seawater, down and re-flooding the Mediterranean basin. So the Messinian crisis involved this strange drying up as a result of the occlusion or the closure of Spain down onto Africa, the Gibraltar Straits, and the Messinian event is this event of drying up where water evaporated out of the Mediterranean basin. All right, now another area that's important. Maybe flip back to this one. I think that. Yeah. Okay. So Africa shows some interesting changes also this time. Of course, it had drifted long ago from South America in the later part of the Cretaceous, but a new rift develops in Africa during the Neogene time, really about 10 million years ago, centered on what we call the Afar Triangle. The Afar Triangle is right here. It is this point where the two corners of the Arabian subcontinent come down. And you have, of course, as you should be able to draw even, if I were to ask you this, the Red Sea arm, the Gulf of Aden arm, and the East African Rift Valley arm to form a three-way triple junction. This is causing the Arabian subcontinent to be pushed off as the Red Sea opens, and as it migrates here, there's a subduction zone in the area of Iran, Iraq, and this region through here, which is called the Zagros crushed zone. And really, this is creating an accretionary wedge push up onto what was once part of Africa here, the Arabian continent. It's being crushed down by an accretionary wedge, meaning that the Persian Gulf is none other than a peripheral foreland basin. This famous, now called Arabian Gulf by some people, but Persian Gulf is the old name. This is a classic foreland basin that developed in this time. So while this is being torn off, this is being crushed over here, formed the Zagros, which is almost a continuation of the Alps back into here. And this is sort of where the suture is. There's our ophiolites through here. They're being scraped off from the downgoing slab, and this is pushed onto the Arabian plate here, forming the Persian Gulf. Here's just a scene. There's lots of very great tectonic activity in this area. Not only is there political strife but this is an area of great danger from earthquakes because there's a tremendous amount of compression. Now, we don't know, of course, which will become the failed arm, if any of these. Maybe it's going to be the Red Sea will become failed eventually if this stalls over the East African Rift Valley. We don't know, can't predict yet, and never we will know, but it's going some way to evolve as those three arms continue to spread again. All right, going further east, we come into the Himalaya area, or Himalayan, depending on who you like to talk to. So, oh yeah, here again is this. There you can see the three arms and the rift. And the Zagros, in a way, continues on eastward into the Himalaya. So, from Alps to Zagros to Himalaya, you have this enormous belt of deformation. India had spun off from Africa in the Cretaceous time, and it made a rather rapid transect. You can see 80 million, 70 million, 60 million, and 30, and then around 20, it's contacting the Asian subcontinent. So during the Neogene, in the early Miocene, this really gets going. And of course, this is just a very schematic thing, but it shows here is the Himalayan suture as India has rammed itself underneath the Tibetan plateau, pushing that thing up. This is one of the rare schools you can actually get to go and see these things, because Lewis Owen does run a field trip every so often to go out and see the amazing Himalayas. There they are. You can click that now. So during this time, we have the Himalayan front developing, the Tibetan plateau pushed up to great heights, Mount Everest, the highest point on the continents, pushed up. It's an enormous belt of deformation occurring in Neogene time, and so big is it that it's changed the entire budget, geochemical budget of the oceans, because the runoff of sediments and so on, for example, has increased the amount of strontium-87 in seawater, which we can see the signature of this erosion. Okay, so how did it go? Well, if you go back into Cretaceous time, here's India coming north. Here's a classic Andean-style orogeny with an accretionary wedge, four-arc basin, of course, and a magmatic arc in where today is Tibet. And now, as we approach the Miocene, as we're into the early Miocene, you see that part of this Indian subcontinent is undertucking the ophiolites of the old accretionary wedge. Here's the remnant of the four-arc basin. And the magmatic arc shuts down eventually. And also, a very interesting thing develops, and I gave you a cartoon, although it's a little bit hard to read, but you should be able to follow it. You can see there is a slice of the Indian crust that cuts across. So you start to tuck one piece of India underneath another. And then even a second slice. So you have the main central thrust and the main boundary thrust stacking up here. And technically, the Sibalics, which I mentioned before, namely because they have the beautiful record of the fossil whales, the Sibalics are really forming in a peripheral foreland basin on the downgoing slab as all this debris coming down off the eroded plateau and the Himalayas. So a rather complicated situation, but you can see how it evolved from a standard Andean-style subduction to a more or less what we would call sort of a Timor arc type subduction, where you have a continent rammed underneath another continent. Meanwhile, Australia and New Guinea are also migrating northward, not as fast. And the Hawaiian chain is forming in the Pacific during the Neogene, although it's not quite fair to say that, because in fact the Hawaiian chain begins in Cretaceous time with Hawaii, the original site up here, and probably a big hotspot burning through, and then the Pacific plate being shoved over that. Here you can see early part of Cenozoic, 60 million, and coming down 55. There was some change, we know, in the movement of the Pacific plate right around 43 million years ago, which caused this elbow bend. This is called the Emperor Seamounts, in case you've forgotten. And then the Hawaiian chain proper, developing 43, 30s, 20s, 12, 10, and so on, right down to the minor. It's a classic Nemataf Thor hotspot track that everyone knows about, but it is probably the prime example of such a thing. All right, let's return to our other side for a moment, the Appalachian side of North America, and see what's happening. Of course, we are passive margin, more or less, facing an opening Atlantic Ocean. Okay, no big deal, there's a mid-ocean ridge. As far as sequences, we're in the last gasps of this weak sister sequence called the Tejas, named for Texas. And it's sort of a regressive phase. We do see, however, some really good sediments deposited during this time. And we see a lot of sediments because just this, during the late Cretaceous and coming into the Paleogene and continuing into the Neogene, the old flattened off Appalachians were rejuvenated. So you're seeing, going from a peneplain in the Jurassic and early Cretaceous, this stuff is starting to rise back up again, isostatically maybe, and as a result, you've got a pretty high relief set of mountains once again in the Appalachian region. And this means that you have a lot more sediment pouring out on the passive margins. It's an unusual passive margin in that sense because it's shifted from carbonates to clastics as not a real tectonic event takes place, but a rejuvenation event takes place. And also, while we're on the subject, and I hope you're taking off all of these key things that happened during the Neogene, another interesting feature forms the Adirondack Dome. I don't think I have a picture, but the Adirondack Dome is here in New York, a circular uplift. It's got Precambrian in the bottom, so you'll say, when I ask you when did it form, you'll say, oh, about a billion years ago during the Grenville. That's when the rocks were metamorphosed, but the dome, the Adirondack Dome itself, that's Neogene. We don't even really understand why that is popping up, but it may have to do with a newly developing hotspot, or a hotspot that was spun off from the Montreal hotspot. Montreal's just up here. But we do understand that even since the 1940s, when they started doing good railroad surveys, that land has popped up substantially, more than just could be accounted for by glacial rebound. So, for some reason, it's being pushed up from below. That's the Adirondack Dome. It's Neogene also. Back to the coastal plains for a moment. Where's Austin? Never here, but I wanted to mention that I put him onto some localities on the coastal plains so that he could collect shark teeth over the spring break, and he did. And the area of the Salisbury Embayment, which is the Chesapeake Bay, and all down through the Carolinas and so on, you find coastal plain sediments, picture please, that show a good record of Cenozoic development in this area. So along this continental edge, you do still have sedimentation, and up into the Mississippi Embayment, partway up as well, and in the Texas coast. This is what we see for the Tejas sequence. There is no Tejas in here, that's all above sea level. But go back to Maryland, okay, and the famous Scientist Cliffs and places like this along the Chesapeake, and you see these spectacular cliffs of soft, unconsolidated sediment. The reason they originally called it tertiary is because it was not actually rock, it's just sediment. And you look in there, well, you look in there and you see a lot of fossils. Pictures of like I said, oh, okay, but I'll show them later. But they're full of fossils, full of a lot of shells and shark teeth and stuff. Going to the Gulf coastal area, we see another interesting region of sedimentation, and that was thick stuff, thick sets of sediments coming down the Mississippi and dumping upon the older deposits that included at the very bottom, well, hard rock underneath, but probably metamorphic rocks and, I don't know, even old Gondwana, I think. But here then, above that, was the Luan Salt. The Luan Salt, you will remember, you won't remember, but I'm telling you, you should, was a Jurassic salt developed in the early Proto-Gulf of Mexico. Now with all this loading of sediment, salt is actually lighter than the overlying sediment, and this area right in through here develops salt domes. You can see salt has a density of 2.2, and these sediments have 2.4. So it's lighter than the sediments, and when you load down on top of it, it begins to rise up in big domes called diapirs, and these salt diapirs are of great importance to us because it's around the diapirs, probably better shown here, that you get fracturing. The strata are dragged up along the side of these salt domes, and petroleum, which is in abundance in some of these Neogene sediments, Cenozoic sediments, rises up till it's trapped against the impervious salt on the edge. You can sort of see that there too. And this means that by getting the seismic profiles of the Gulf of Mexico, they could see where salt domes are located. There are also some up in Louisiana. And they drill them, and here you find a rich source of petroleum, which is trapped by the salt domes. All right, now to the Great West. So the next 15 minutes at least I'll have to devote to the evolution during Neogene time of this great region here. You can see all the black is volcanics. There's a lot of volcanics, none in the Colorado Plateau area. Here's the area of the Tejas sediments in gray. You see, that's the stuff we were just talking about, where the salt domes develop, and a lot of shell-rich sediments accumulate. But here, volcanics and uplift. Lots going on here. Just to point out, the setting and critical feature that has to be understood is really what happened along our west side. Okay, click down for a moment. Thanks. And here you see a late Paleogene, that's the Oligocene age, Oligocene epoch. And you see here, there is a strange view, but there's San Francisco. Here we're along in parts of what are today California. There's subduction all the way along. It's Andean, no problem. But you can see what's coming, because here is the Farallon plate. Here's the Pacific plate. There is the so-called mid-Pacific rise. Well, by this time, the rate of subduction was sufficiently great that it had consumed almost all of the Farallon plate. And that's going to bring the mid-ocean rift right up against California, or part of what's today California. And so you have now established by early Miocene a new regime, whereas had been completely Andean before, just subduction, accretionary wedge and all that stuff. Now you have the collision with an oblique corner, an oblique collision with a corner of the Pacific plate, and a little remnant still here of the Farallon, and a little remnant of the Farallon down here. Okay, there's the so-called Juan de Fuca plate, and down here the Cocos. As things developed, instead of continuing to subduct the mid-ocean ridge here, because of the oblique nature of the collision, a long curving transform fault, which separated this rift segment from this rift segment here, began to evolve, and it began to elongate along through California. This is the San Andreas. The San Andreas transform resulted from the oblique collision in Miocene time of the Pacific plate and the Farallon with North America. And you can see that. So you've got this little remnant down here of the Cocos plate. You got this remnant down here of the Juan de Fuca plate off Washington and Oregon. And in between, an increasingly elongate and complex nest of transform faults that are everybody's most famous example of a transform fault, even though they're an extraordinary, weird example, because normally the transforms are just connecting one segment of mid-ocean ridge to another one. But here they do that, but across part of a continent, and that means that this westernmost part of California is actually physically attached to the Pacific plate and is actually shifting in a northwestward direction at a rate that people say in the future Los Angeles in a couple, well, not more than a couple, but so like 10 million years, then Los Angeles will be right up snug against San Francisco. So this is a very interesting thing. Now, the critical point, however, that I'm really evolving toward is how does this influence all of this? And one way we can say it is that we stopped subduction here. There had been, as you know, or should know, there had been a very flat plate of the Farallon and underneath North America. And it was still there, but it's no longer subducting starting in the early Miocene time. So what happens is that plate cools, and as it cools, it probably delaminated and pulled away from the North American crust. And this may have even been successful in tearing off part of the basement underneath North America. So this is a very interesting development. What it really means in essence is whereas that plate has been tugging down and pulling down on the crust, it now subsides away and the crust isostatically pops back up. I think therein lies part of the explanation for this whole region. An isostatic regional uplift that occurs following the end of subduction in California. In addition to that, there's a shear movement going on. You're shearing one plate against another. And some people, at least, have argued that this has to do with the accordion-like opening of a very broad, interesting region, which since Miocene time has doubled its width. It's